Alright, section 12-4 is general curvilinear motion, and so here curvilinear is the key word. We're talking about a curved path. We will then, in subsequent sections, talk about different coordinate systems. But for right now, we're just going to talk about some basic definitions. We're going to go from position to acceleration. So let's start with very important position. Let's say we have some curved path. And let's call this path S of t. It's curved, so it's a arc length or something like S, and it's a function of time. We have some reference point we can refer to, and we can place an object somewhere on that path because something's moving on there, and make a vector to that object and say that this vector is a position vector r. That describes the position at any given time t on the path S of t. Okay, so that makes r a function of t also. We're going to need this because sometimes we're given the path that the particle takes, and we can integrate and differentiate to get the acceleration or the velocity depending on what we're given. Excuse me. Okay, so now let's say this thing moves over to here. It moves over to some r prime. That means it moved over some delta r by vector subtraction. And from vector subtraction, we could say r prime is equal to, well, this is addition first, r plus some delta r. Right, we get this vector right here by taking this vector and adding this vector to its tail. And that's one way of writing it. This one makes a little bit more sense to me sometimes. Or, yeah, this one. R prime minus R. Okay, so it all depends what you need and what you're solving for and what you're given. Same thing, we're just rearranging terms. But basically, some time interval's gone by, delta t, and that gave us some change in position, right? Some time had to have gone by for this to occur. And we call that delta r a displacement. Okay. Now, if we wanted to look at the instantaneous velocity, it's usually more important than speed to us. When we talk about energy methods, speed will be important, but we'll still get that from the instantaneous velocity. So the instantaneous velocity would be first taking our average velocity, which we saw before was just how much it moves over the time elapsed, in this case delta r over delta t, and taking the limit as delta t approaches 0. And that's going to give us our velocity vector. And we can call that dr dt. So that's one important definition, or just the v is equal to dr dt. Okay. What's interesting and needs to be known as a fact is that if we look at that same image, and here's where the particle is on its path, its velocity will always be tangent to the path. So we could also say that if we wanted its speed, the velocity would be the same. If we wanted its speed, we could find it by taking ds dt also, if we knew s is a function of time, right? So we can get velocity either way. Alright, let's take this one step further. If we have a path and at one point it has some velocity, and at another point it's got some other velocity. Notice they're both tangent. We'll call that one v prime. We can say that v prime is equal to v plus delta v. So it had to have some delta v vector to give it some oomph and move it in the other direction, and that comes from an acceleration usually. We can say that the average acceleration over some interval delta t would then be taking that delta v and dividing it by that delta t. Ta-da! You've seen most of these before. We can take the limit of that as delta t approaches 0, like we did with the others, and get that the acceleration is equal to dv dt, the time derivative of velocity. We can also write that as the second derivative of position with respect to time. Okay,